Download this code from codegive.com, link in the description below. OK, let's dive into the concept of grammar ambiguity and how to demonstrate it, complete with explanations and code examples. Understanding grammar ambiguity. A grammar is considered ambiguous if there exists at least one string, or sentence, that can be derived in multiple distinct ways according to that grammar. In other words, there are two or more different parse trees, or derivation trees, for the same input string. This ambiguity can lead to problems in parsing, compiling, and interpreting programming languages or any formal language. Why ambiguity matters. Ambiguity can cause serious issues in computer science. Parsing errors. A parser, which analyzes the structure of a program or sentence, might not know which parse tree to select, leading to unpredictable or incorrect results. Different parse trees might imply different meanings. Compiler/interpreter confusion. A compiler or interpreter that uses an ambiguous grammar might generate different machine code or execute different actions depending on the chosen parse tree. This makes the behavior of the program unpredictable and unreliable. Language definition problems. If a language's grammar is ambiguous, it becomes difficult to define the precise meaning and structure of the language. How to show ambiguity. The standard method to prove that a grammar is ambiguous is to 1. Find a string. Identify a string that you believe can be derived in multiple ways. This often involves strings that contain operators, conditionals, or other features that can be interpreted in different orders. 2. Construct two, or more, parse trees. Build at least two distinct parse trees for the same string using the grammar's rules. These parse trees should represent different derivation processes. 3. Present the parse trees. Clearly show the parse trees, explaining how each tree represents a valid derivation of the string according to the grammar. 4. Derivations. Sometimes it's easier to show leftmost or rightmost derivations to showcase the different application of production rules, which leads to different parse trees. Example 1, Arithmetic expressions. Let's look at a classic example of an ambiguous grammar for arithmetic expressions. Here, *e represents an expression. *ID represents an identifier, example a variable name or a number. *+ and * are addition and multiplication operators. The ambiguous string *ID plus ID *ID. Parse tree 1, multiplication first. This parse tree corresponds to the expression ID plus ID *ID. Parse tree 2, addition first. This parse tree corresponds to the expression ID plus ID *ID. Code example, Python. While we can't directly run a grammar and get it to produce parse trees in the same way we run a program, we can use Python, or another language, to represent the grammar and simulate the generation of parse trees. Explanation of the code *. 1. Parse tree node class *. This class represents a node in the parse tree. Each node has a value, the non-terminal or terminal symbol, and a list of children, the subtrees. 2. Build _parse _tree _add _first and build _parse _tree _multiple _first functions *. These functions manually construct the two different parse trees for the string ID plus ID *ID. They simulate the application of the grammar rules to create the tree structures. They take in an array of ids, again a simplification. 3. Printing the trees *. The _str_str__ method in parse tree node provides a simple way to print the tree structure in a hierarchical format. Demonstrating ambiguity, formal proof. To rigorously demonstrate that the grammar E-E plus EE** EID is ambiguous, we would present the two parse trees, as shown above, and explain how each tree represents a valid derivation of the string id plus id asterisk id according to the grammar rules. We would also point out that the different trees lead to different interpretations, i.e., different operator precedence. How to resolve ambiguity? Since ambiguity is undesirable, we need ways to modify the grammar to make it unambiguous. Here are some common techniques. 1. Operator precedence and associativity *. The most common way to eliminate ambiguity in arithmetic expressions is to enforce operator precedence and associativity directly in the grammar. For example, in this grammar, *E represents an expression. *T represents a term, multiplication. *F represents a factor, parenthesized expression or identifier. This grammar enforces multiplication to have higher precedence than addition. Parentheses can still be used to override the default precedence. The E-E plus T rule means that addition is left associative, grouping from left to right. Similarly, T-T** F ensures left associativity for multiplication. 2. Disambiguating rules * introduce specific rules to guide the parser's choices when faced with multiple possible derivations. These rules can be based on syntax or semantics. 3. Rewriting the grammar * sometimes, a complete restructuring of the grammar is necessary to eliminate ambiguity. Example 2, dangling else. Another common source of ambiguity is the dangling else problem in programming languages. Here, *S represents a statement. *E represents an expression. *Other represents some other statement. The ambiguous string * if E1 then if E2 then S1 else S2. Parse tree 1, else matches inner if. This interpretation associates the else S2 with the inner if E2 then S1. Parse tree 2, else matches outer if. This interpretation associates the else S2 with the outer if E1 then. Code, Python, illustrating the tree structure, not parsing. Resolving the dangling else ambiguity. Most programming languages resolve the dangling else ambiguity by adopting the convention that the else clause is always associated with the nearest unmatched if. This can be enforced in the grammar by rewriting it, although the rewritten grammar may be more complex. This grammar separates statements that contain an else clause, s_with_else, from those that don't. Key takeaways. Ambiguity is a property of a grammar where a string can have multiple valid parse trees. Ambiguity can lead to parsing errors and unpredictable behavior. To prove ambiguity, find a string and construct 2 or more distinct parse trees. Ambiguity can be resolved by rewriting the grammar, introducing precedence rules, or using disambiguating rules. Programming language grammars are carefully designed to avoid ambiguity. I hope this comprehensive explanation, along with the code examples, clarifies the concept of grammar ambiguity. Let me know if you have any more questions.